Hello, welcome again. Today we're looking at transaction management and concurrency control. So basically when we're talking about transactions, we remember we said from our previous classes that a transaction is basically a unit of work. However, if you look at the unit of work within it, it has several other tasks. And these tasks must be performed to completion before we can say that the transaction has been executed to the very end. So it basically deals with problems of having to keep the database in consistent state. And remember, a database that is not in consistent states will always will make us have the wrong kind of data in our database. So it is important to point that the database should be consistent when a transaction has terminated. And that is the reason why if we are having a transaction as a unit of work and we have other sub-units within that particular transaction, they must all execute to the end before we can say the transaction has completed. So as you can see, it's series of actions and they must be carried out to completion. So as you can see, it's a series of work that must be carried out by a single user or application program. And therefore, that's what we're saying is treated as a logical unit of work. And as is being treated as a logical unit work and executed to the end, then we must ensure that there is consistency. It will basically transform the database from one consistent state to another consistent state. Now, looking at this is an example of how a transaction would appear like in SQL. Now, consider where we have a table we are referring to as project. Within that particular table we are referring to as project, there are columns such as budget and there is P name. So if we would wish to change the value in budget by making an increment by 10%, then basically these are how we need to go about it. As you can see here, we have set budget is equals to budget multiplied by the value that is already in that particular budget and then a 0.1, where P is equals to engineering. So we are basically changing all records where P name is equals to engineering to the value that is there and by a 0.1 also. This can be translated in transaction as follows. So if you look at it from the perspective of a transaction is always begin. A transaction will have begin and it will have an end. And then there will be the SQL that needs to be executed, which is our original SQL. So for it to work as a transaction, it must have a beginning and an end. Because within where we have our execute SQL, we could be having many SQL statements that require to be executed. But it is when all these SQL statements have successfully executed, that is only when we can end. And when we end, in most cases, we do what referred to as commit. So really, what is a transaction? So this can be any request to either read or write to a database, and it may consist of a simple SQL statement that is for purpose of selecting, for purpose of updating the records in the database, and insert, and can be even a combination of select, update, and insert. So as we have said, it's a logical unit of work, but you must understand that we have said that within that logical unit of work, we have other subtasks, and they all must be executed to completion. And that is the only reason when now we can be able to talk of the database being in a consistent state, because we are moving from consistent state, remember, to another consistent state. Most real-world database transactions are formed by two or more database requests, because see, a database is a shared resource. We are sharing data that is in a database, and that's the reason why we are having a database in the first place. We have different users who fetch, who update this particular data, and they all need to have their transactions executed to the very end. Now here is an example of a relational schema for a sales company database. So we say the schema is more of, if you look at the database and then the tables within that particular database and how they are related to one another. Like this is a database that has 6 tables. Now we have customer, invoice, line, product, vendor, and then account transaction. All these tables are related. Customer number related to invoice, also related to accounts transaction. Invoice related to line. As you can see, we are forming, for us to be able to create these relations, we are forming foreign keys, because customer number is a foreign key in accounts transaction here. We have invoice number, which is also a foreign key here. And then we have product number for product table, product code for product table, which is also a primary key here. And you can see we have shown the cardinality. The relationship is one to many, one to many, one to many. From product is one to many, and also from vendor is one to many. So if you create such kind of relationship in using the relations that you have in a database, then you've come up with a schema for your database. So you must understand that we basically not all statements, SQL statements that we'll be executing will be able to update the database. However, we must understand that if a transaction would leave if a transaction would leave the database incomplete, then there would be a problem, because this could lead now to the devastating effect of integrity, because we do not have that consistency. We can have enforcement constraints where basically you can have like if you have a foreign key enforcement or constraints, you can declare that data in foreign key data in one relation cannot be deleted when we have its primary key on another relation that has not been changed, so that you can restrict change of that particular data. And also we can say that the database management system has a way also of protecting the data that we have in the database. So when you are processing transactions, we have various ways that a transaction can be executed for purpose of creating, inserting, decreasing, updating, creating, and this is basically the CRUD that we talk about in database system, CRUD. A transaction can be able to perform that. So if the system fails between the first and the last step, basically then we're going to have an inconsistent state, and therefore should it fail, then we should not allow it to commit. And in most cases, what would happen is that it will roll back. Rolling back would mean that all these other SQL statements that have been executed to completion will have to be reversed, so that we can return back to the initial state before the transaction started. Transactions must be able to fill their ACID property. And the ACID property, basically, we are talking of atomicity. Atomicity is one of them. And under atomicity, basically, we say that we require all operations of a transaction to be completed, because a transaction is a logical unit of work and it's atomic in nature. And therefore, for that reason, we must have the whole of it executed to completion. It cannot be partially executed. Now, once executed to completion, then we have that durability, because what happens is that now what we need to do is commit that particular transaction. Once committed, it basically implies that we cannot be able to reverse. And we have C standing for consistency. Sometimes we talk of serializability. So basically, it's all about after all those transactions have been executed, it's ensuring that we can be able to leave the database in a consistent state, because we said we begin from a consistent state to another consistent state. While in isolation, once we have a transaction, that transaction should not be able to rely on other transaction for its execution, and there should not be any other transaction that would rely on that particular transaction. So every transaction stands on its own. It's a standalone transaction. It must be completed in isolation, must be executed to the end. Under transaction management, there has been some standards that have been defined by bodies that do govern SQL, and we have ANSI as one of them, and they've provided support for two SQL statements, that is commit and roll up, because remember we said that commit is when the transaction has executed to the end, then we make it permanent. That is, once we commit, it cannot be reversed. However, if you're having a transaction executed and then somewhere in between something happens such that the whole of transaction is not executed, then what we do is that we roll back. Rolling back means going back to the original state. If there are other SQL statements that within that particular transaction that had already been executed, then we will have to reverse all those changes that came as a result of execution of those SQL statements. So it's required that once we start a transaction, we must execute it to the very end. Now we have 4 things that we must consider in transaction management. First is the commit that we've just talked about, where we make the changes permanent. Then we have the rollback. Rollback is if we are unable to execute the transaction to the very end, then we must reverse. That is, we abort the whole process. Then we have the end of the program is successfully reached. We say basically just commit. If the transaction does not execute to the end, then we roll back. Then a rollback occurs. Now, all transactions keep what we refer to as a transaction log. A log is basically a record of what has been happening during those executions of transactions as people are accessing or systems are accessing the database, making use of the data within that database, updating that data, and so on. So transaction log would record the beginning of a transaction. And we can have the type of the operation that was performed. We can have a name of the object that was affected as the transaction was being executed. We can also be able to keep a picture of before and after. And at the end of it, once executed to the end, then we can commit. So basically, these transaction logs help us at the end to be able to, should something happen to the data that we have in the database, then we can be able to restore this data from the picture of before that we are talking of. Hence, any corrupt data can be restored. So we keep the logs more like it's a database of some sort. Should there be any error that would occur, then the database management system can be able to look at the logs and then it can be able to reverse back, because we are saying if a transaction is not executed to the very end, then we can reverse. Then how do you reverse, especially for some SQL statements that you had already executed to the end and they were able to update some records? Then it's looking at the transaction logs and can be able to fetch the original or the value that has been changed from the transaction log and then replace it with the new values that were introduced in the record. That way we are able to restore, or we are able to move back to the original state. And basically we say that the transaction log is more like an extra database itself for your particular database. Okay, let's look at the following example. This is an example of a transaction log. You can see we have records 341 all the way to 362 transaction IDs, and we have transaction number 101. You can see we have, at that particular time, we have start of the transaction. Then what has happened? Once we started, we updated a table that we refer to as product, and this row was affected, row ID, and the attribute that was affected was product QOH. The value before was 25. Now the value after is 23. Again, we proceed with updates, another table, customer ID. As we update the customer ID, what's happening? We are changing the customer balance from 525.75 to 615.73. And then we end that particular transaction. That transaction only ends if we are able to do the commits. Now, concurrency control is something that is very important when it comes to distributed database systems and management of transactions. The objective would be to ensure serializability of transaction in a multi-user database environment. So if we have in a multi-user environment, we basically say that it's possible for transactions to create several data integrity problems and consistency problems, and we are looking at them from these 3 main problems that might occur. We have lost update, uncommitted data, and inconsistent retrieval or analysis of data. Let's look at it via these examples. Now here we have transactions. We have 2 transactions here, transaction T1 and transaction T2. Now here are the steps: read product QOH, stored value is 35. Product QOH, we have an increment of that by 100, and then we write 135. we have allowed transaction 1 to execute to a point of writing a value in product QOH. Then we have transaction 2 happening where we are reading product QOH. Now it is reading and the value is now 135. So it's reading the current value, which is 135 as opposed to 35. Then it's doing some computations here. There is a deduction of 30 from 135 and then dating the value there by 105. So these are two transactions that have occurred sequentially. That is, first transaction T1 it's allowed to execute to the very end. Then we have the second transaction T2 is allowed to also transact after transaction 1 and to the end. Now we can have a scenario of lost update if we look at those two transactions from this perspective. We allow transaction 1 to make a read of PROD or product QOH, the value is 35. Then at the same time, transaction 2 is also making a read of the value that is stored in that attribute as 35. Then T1 goes ahead and makes an update of the value by an addition of 100. Then T2 itself makes a deduction of 30 from the value it originally read, which was 35. Then we have T1. What will happen with T1? T1 will write value 135 because it basically has made an addition of 100 to the 35, so we have 135 there. What about T2? T2 goes ahead and performs its transaction, which is 35 minus 30, and that gives us a 5, and then it updates that particular value. As you can see, we have a lost value. So that's a problem that can occur in a multi-user environment, and this value has been lost because these updates cannot happen. This update, it was updated, but this is not the current value that is there. The current value that is currently there at the end is 5. Compare that with what we originally saw, that we are supposed to have a current value of 105, but we have lost the 100 and we now have 5. So that's an example of lost updates. So what would be the solution to ensure that such a problem does not occur in the future? The solution would basically be to prevent transaction B from ever starting until transaction A has completed has made its update and completed that particular transaction. So you can lock transaction B and prevent it from executing. What about the uncommitted data problem? Every transaction must stand on its own and must be able to execute from the beginning to the end without relying on any other transaction. So in such an environment would be violating the isolation property. Here we have an example of that. Let's see. We have two transactions here again. Transaction 1, T1, transaction 2, T2. So we begin by reading prod QOH 35. Then there is an addition of 100 to the value 35 we've just read. Then there is a write. We write that particular, or rather we update prod QOH with 135. Then instead of committing, what happens? There is a rollback. So this value has been rolled back to its original value. Then we can have now transaction 2 reading what value? The value that has been rolled back, because the current state of prod QOH is 35 and that's what it has read. And then it can continue ahead by doing what? Maybe making a deduction of 30 and then writing the current value, which would be 5. That's what we would expect to happen in normal execution. But let's see what happens now if we have uncommitted data problem. We can begin here where we have transaction 1 making a read, 35, and then making an addition of 100 to the 35 and then writing the final figure, which is 135. These data, these 135 is yet to be committed. Remember we said to commit is to make it permanent. T2 goes ahead and reads that value before it has been committed. Then T2 proceeds to make its deduction. At this particular time now, this is when transaction 1 has decided not to commit but to roll back rolling back to the original value, and therefore we have the original value is 35, but we can see now transaction 2 writes 105 as the current value and probably goes ahead and commits. That way we have what we refer to as an uncommitted data problem, working with data that is not real, not the actual value, not the actual final value, and that is the uncommitted data problem, will result to such kind of scenarios. Now let's read this. We have scheduling of surgeons for operations. Like we have transaction A reads uncommitted update at T2 time, that is assigning a theater to surgeon and a patient. The update is then undone at T3, that is surgeon or patient become unavailable, while transaction A is therefore operating on false assumption that is transaction A becomes dependent on uncommitted updates at T2 time. And that is the challenge that you can have in database systems. If data is yet to be committed while you go ahead and read that particular data, you'll be working around, you'll be working on false information. What would be the solution to uncommitted data problem or dependency problem? So it would be basically to prevent transaction A from reading the value of that particular relation until the decision has been made to either commit or abort. We have the third problem, which is inconsistent retrieval problem, and this would result in some data being read before it can be committed, others being read when it has been committed, and as a result of that we can have inconsistencies. Okay, let's look at this example. Now here is an example of what can happen. We have transaction 1, which reads or rather calculates the total of the values that we do have within that particular prod QoH attribute. And then we have transaction 2 going ahead to make changes to those particular values. You can see there is an increment of 10 where we have a product code 1546 QQ2, and then we have another record being updated with a deduction of 10, that is where we have product code 1558 QW1. Now if these values were different, then that would imply that the total being held by T1, transaction 1, is inconsistent. That value, or rather this SQL statement was executed after transaction 2 had completed and committed. But luckily, what we have in here is we have an increment of 10 and then we have a deduction of 10, which now leaves us having the same consistent figure. But if they were different, then they would have a problem, because this shows you that is basically what happened. We did the totals here. This transaction 1 got this total 92, and then we have transaction 2 which affected these two records by making an increment here and by making a deduction here. But luckily the value is the same, and therefore we have the same figure here, which is consistent basically. So we were saying if the value was different, then we would have a challenge, especially if we had an update on this particular record, that is QQ2, and then we never had this update on 1558 QW1. We would have the wrong figure here. And let's look at another example of inconsistent retrieval. Here we have in transaction 1 making a read of these particular attributes, prod QoH, and where product code is 11QER and 13Q2. And then the values that we have are, we have 8 and then we have 32. So if you get a total of that, gives you 40. We have another transaction here, transaction 2, making a read of this particular record where the prod code is 1546 QQ2. It's getting 15, and then there is an update of that 15 with 10, and then there is a write where now the value is 25. We come again to transaction 1. Now transaction 1, what it does is that it reads the QQ2 again, where now the value is 25. It has been updated by transaction 2, and then it also goes ahead to read 1158 QW1, which is 23. It's making a summation, and therefore, as you can see, we have an increment again from 40 to 40 plus 25 gives us 65. 65 plus 23 gives us 88. Then we have transaction 2. It proceeds to read another record again. Here we have 1558 QW1. It's a 23. And then it goes ahead and makes a deduction of that value and then writes or makes an update of that value. Now it's 13, but remember it was read by transaction 1 as a 23, but now it has been updated as a 13. And transaction 2 goes ahead and makes a commit. It says that's the permanent, that's permanent, and that's the final value of 1558 QW1. But remember, transaction 1 read it as 23, but supposed to be 13. So again, we have a read of record with product code 2232QTY8. And it keeps on doing a summation, and then that is basically 88 plus 8 gives us 96. And then again, it reads another record 22, the one with product code 2232QWE. And then it makes an addition of 6, and therefore now we have 102. Well, this figure is wrong because remember, the value that we have in prod code, that is prod QOH, where the product code is 1158 QW1, is not 23, but it is 13. It has been updated to 13, and that way we basically are having what we refer to as an inconsistent retrieval. Transaction 1 is operating with the wrong data. Now what would be the solution? The solution again will be to prevent transaction B from reading the balance of account 1 or account 3 until transaction A has completed. Generally, you get the flow of what we are trying to say. Every transaction must first be allowed to execute to the very end before any other transaction can make use of the data it's operating on. Now let's look at database management system components. Now we have the transaction manager, which basically is within the database management system and will ensure that transactions do not interfere with one another or corrupt the data in the database. Now, next we have the schedule manager, which sometimes we do call the lock manager. It implements a particular strategy for concurrency control, basically using locks as a means of managing concurrency. And then we have the recovery manager. It basically is used to restore the data that we do have in the database, can take it back to the picture of before, should an abort process have occurred. And then we have the buffer manager, which helps us to be able to transfer data from memory to storage. So let's look at the scheduler or the lock manager as we know it. So this will ensure we have serializability and isolation of transaction. So it controls algorithms such as locking and timestamping. And for that reason, it's able to ensure that the CPU is efficiently used and also ensure that there is isolation. That is, it will facilitate isolation to ensure two transactions do not update the same data element before one transaction can be able to commit. Now remember, we have what we refer to as readers and writers, because we have different transactions that are accessing the database, and therefore we can have a control where we have when transaction 1 is reading, then we can have another transaction reading. We do not have a conflict there. That is, we say that we can have many readers, but we cannot have readers and writers at the same time. And that's why when transaction 1 is reading and transaction 2 is reading, there will be a conflict. When transaction 1 is writing and transaction 2 is reading, there will be a conflict. When transaction 1 is writing and transaction 2 is writing, there will be a problem. That's why I'm saying we can have many readers, but we cannot have many writers, and we cannot have readers and writers at the same time. Now, concurrency control with locking methods, how does it operate? So we have locks that will basically ensure that we have exclusive use of data items to a concurrent transaction, to the current transaction. So we have lock that would prevent other transaction from accessing data that is currently being used by a particular transaction. Like we can have transaction 2, which does not have access to data items that is currently being used by transaction 1. Now, and remember, we have seen that is one way for us to be able to prevent the 3 problems that we have just seen. So we basically just need to prevent another transaction from reading inconsistent data until this data has been updated. That is when we can allow maybe transaction 2, transaction 3, and so on to read this particular data. So the lock manager, which is a scheduler, now will be able to assign, come up with policies for locking data that is being used by different transactions, or that is being used by a current transaction that is being executed. We can have a lock granularity, where basically we can make locks based on different levels. Like we can have database level lock, we can have table level lock, page level lock, row level lock, field level locks. That is basically you can either lock the entire database, or you can just lock a specific table and allow other transactions to access other tables, or you can lock a page, that is an entire disk space can be locked, or you can lock just rows of a particular relation and allow other rows to be accessible to other transactions, while these particular rows that you have locked, they are being worked on by a particular transaction. The picture here shows us basically a database level locking sequence. If you look at it, we have a transaction 1 here. We have a lock of table A such that it's only accessible maybe to transaction A, while we have transaction 2 trying to update table B, but it cannot update table B, though table B is not in use by transaction 1, but it cannot be able to access it. It has to wait until transaction 1 has completed the update of table A. Then we can have now we can have transaction 2 okayed to go ahead and make use or access table B. And our table level locks basically again is the same kind of scenario here. Now we are looking at it from the perspective of a table. Now we have transaction 1 that wishes to update row number 5. I'm guessing this one could be the row number 5, maybe somewhere here. But we also have a transaction 2 which wishes to make use of the same table A but to update row number 30. But transaction 2 has to wait until transaction 1 is through with its updates. You can see at time 6, that is T6, we have unlock end of transaction 1. Then now transaction 2 can be okay to go ahead and make use of this particular table. But remember, as transaction 2 now gains access to table A, what happens is that now table A is locked and no other transaction can be able to access it until transaction 2 is through with this particular table. Now for page level lock is more of the disk space. We are looking at disk space that will contain our data. Therefore, we have transaction 1 updating row number 1, and therefore that particular page can be locked. Once locked, it can only be unlocked once transaction 1 is through with that particular page, and then now we can have transaction 2 go ahead and make its updates. Now for row level lock is where we are looking at the same table, but you see transaction 1 wishes to update row number 1. So it is only row number 1 that will be updated, so that should transaction 2 also require update of row number 2, then it can be allowed to have access to row number 2. And at the same time, that row will be locked for transaction 2. Row 1 will be locked for transaction 1 until transaction 1 is through with row number 1 is only when another transaction, probably maybe there is a transaction 3 that is interested in making access to row number 1. It is only when that it can be able to access. The same applies to what we have here. So and that's why you see now it will be okay for any other transaction to maybe access row number 3 because only row number 1, number 2 are being accessed. Now, for feed level locks, this one we're basically looking at a situation whereby we can allow transaction to basically access the same row. Remember, row is a record as long as they require different fields or different attributes within that particular row. So this one is also even much more efficient. This will enable other transactions to be able to even process the same kind of record as long as they access in different fields. Now we have the binary locks. And remember, from when we're talking of binary, we are either talking of zeros and ones. And here, one would represent a locked and zero would represent unlocked. Like in the examples we were looking at where prod QOH was being accessed by two different transactions while the data had not been updated, and you saw that we had a problem of lost update. Now that can be prevented by enabling, or rather ensuring, that we have a lock at that particular field. So looking at this table, it shows us an example of what we are talking about. We have transaction 1, that is T1, and we have transaction 2, T2. So we have an access of that particular relation that we are referring to as product, and then a read of that particular field, prod QOH, which value is 15, and then we have an update. It's updated by 10, and now it's 25. And then once it has been updated and a commit has been done, then it can be unlocked now. And that is the only time after it has been unlocked, transaction 2 can be allowed to make a read of that particular prod QOH attribute and now get a value that is, now this value is supposed to be 25. Yeah, there's an error there. This is supposed to be 25, and then it will be 25. You subtract 10, and then you're able to get a 13, and then it can be unlocked at that particular time. So make a note of that this is supposed to be 25 because it's reading this value here. So it's 25, not 23. Now we have exclusive locks, and these are basically used where there is a potential for conflicts, because we basically say that only one and only one transaction can be allowed to have exclusive lock of a particular data item in a record. So it's granted if and only if no other locks are held on that same particular data item it wishes to maybe read or it wishes to make a change to. Then we have the shared lock. Now remember what we said, we can have many readers but we cannot have many writers. And it is for that reason where we can have a shared lock when transactions are just reading that particular data. So many of them can read the same data item, but they cannot read that particular data item when it is being changed. That is when we have a write process going on. So it increased overhead. It leads to increased overhead. So we have three lock operations that do exist. We have read lock, we have write lock, and then we have unlock to release that particular lock. So it can also bring about two problems. That is, the resulting transaction schedule may not be serializable. The schedule may create deadlocks because we create deadlocks where we are all trying to access an item that is being held by another process. And that process is in need of another item that is being held by another process. So that might lead to deadlock. So to ensure there is serializability, then we can introduce what we refer to as a two-phase locking. Though it does not prevent deadlock, but at least it can guarantee serializability. We have the growing phase and then we have the shrinking phase. When you're talking of the growing phase, transactions would acquire all the required locks without unlocking any data. The shrinking phase, here a transaction would basically release all locks and cannot obtain any new lock. For it to work, it's basically governed by the following rules. Two transactions cannot have conflicting lock. That is, we can't lock on the same data item. No unlocking operation can precede a lock operation in the same transaction. And no data are affected until all locks are obtained. That is, until the transaction is in locked point. That is, if the transaction is making use of two or 3 data items, then they all need to be locked before it can start its execution. Here's an example of tool locking protocol, how it basically works. We have start, can acquire lock there, can acquire another lock, and keeps on growing by the number of locks that are being acquired until it has acquired all the locks it requires. Then we can begin to relinquish these locks as we continue to process this particular data, or as the transaction proceeds with its process. So at that particular time when we are releasing these locks, we are moving from the locked phase to shrinking phase, because we are now reducing the number of locks that our transactions currently having. What about deadlock? Here we can have deadlock when we have two transactions that wait for each other to unlock data. T1 needs data item X and Y. T needs Y and X. Each get the first piece of that data, but when they wait to get the second, which the other is still holding, then that leads to that scenario of deadlocks. In other words, what we are basically saying is that there is this transaction T1 that is holding X and Y, T that is holding X and Y also. That is, if transaction 1 releases X, remember T also requires Y. If transaction 1 needs X and Y, and transaction T needs Y and X, so we can have a situation whereby when Y is released, then transaction T can get Y, but X has not yet been released, and therefore it can proceed until it is released. So for these two kind of transactions, then we can have a deadlock situation. So it occurs as a result of maybe one of them trying to get an exclusive lock, and we get an exclusive lock when we want to do a write. So how do we control this deadlock? We can have a prevention, detection, and avoidance. That will help us be able to avoid the deadlock. Here's an example through a table. Let's look at this. We have transaction 1, which has locked X. We have transaction 2, which has locked Y, which is okay at that particular moment. And at the same time as transaction 1 has locked X, we have data item X, which maybe now is unlocked, and data Y is also unlocked. So at time 3, we have T1 has locked Y, and it's waiting. It's waiting for locked X, and it has locked Y. So both X and Y are locked. We have T2, which has also locked what? Locked X, and it's waiting. So they are all waiting. All these transactions are waiting, but at this particular moment, none can proceed because they are all waiting for the other piece of data. They all need X and Y, but they cannot proceed because if you have the X, then you need the Y. The Y is locked. You have the Y, you need the X is locked. And that results in a deadlock situation. So we can introduce concurrency control with timestamping methods. That is where we basically just assign global unique timestamp to each transaction. Also produce an explicit order in which transactions are submitted to database management system. And this now brings the uniqueness that to ensure that no equal timestamp values can exist. Monotonicity ensures that timestamp values always increase. If you're increasing that value, then these values, that is the timestamp value, will not be the same. However, we have a disadvantage that each value stored in the database requires 2 additional timestamp fields, that is for the last read and the last update. We have a wait, die, and won't wait scheme that can be applied. For wait die, that is wait or die, all the transactions wait and the younger is rolled back and rescheduled. We are trying to avoid deadlocks. Won't or wait, all the transactions roll back and the younger transactions reschedules it. So in this kind of scenario now, we'll have each lock associated with time, and that this can guarantee that it's possible for you to get a resource that you require. That is, a transaction can get a resource it requires and if it cannot get the resource that it requires, then there will be a timeout. Through that timeout, if time expires, then it has to release the resource that it was currently holding. And I'm talking of resource in terms of the data that is holding, waiting for another data. Let's look at this example. So here we have a situation whereby the assumption is that this one is older than the other one. So here we have T1 waits until T2 is completed and T2 releases its lock, while won't or wait scheme T1 preempts or rolls back the T2 transaction and it is rescheduled some other time using still the same timestamp. If we're looking at it from this particular perspective where transaction T2 is making a request for a lock and it is holding some data, then we can have, especially the data items is being held by another transaction, then we can have T2 rolls back and then T2 is rescheduled using the same timestamp, and under won't or wait, T2 waits until T1 is completed and T1 releases its lock. So that's a system that enables us not to have a deadlock situation. Now we can have concurrency control with optimistic methods. So this approach is basically very optimistic. It assumes that there will be no conflict and that would not require the use of locks or timestamp. And the main idea is to wait until a transaction has executed to the end, and then it can be able to commit. Very optimistic. And it's acceptable for most read or query database systems that require few updates transactions. Concurrency control with optimistic methods, we have three of them here. We have read phase. So under read phase, we basically are saying that we need transaction to read the database and execute the needed computation and make the updates to a private copy of the database. These are temporary update files which is not accessed by the other transactions that we do have running. While the validation phase, so a transaction first must be validated, and you validate it to basically just ensure that it will not affect the integrity of the database. So if it gets a positive validation report, then it can go ahead and we can go ahead and execute that particular transaction. Under the writing phase here, we are basically committing the transaction, and that is make everything permanent now. Let's look at database recovery management. Database recovery, we are basically looking at a situation whereby the database is in an inconsistent state, and therefore what we basically want to do is take it back to consistent state, because with transactions we say every transaction should take the database from a consistent state, and after it has been executed, then the database should also remain in a consistent state. And that is why if a transaction cannot be completed, then it must be aborted. And as we abort, we basically undo everything that transaction, all the changes that transaction was able to effect, we undo them. Now, transaction recovery will basically generally make use of deferred write and write-through techniques. And what are the deferred writes and write-through techniques? Now, the deferred write, just as the name implies, we defer. We are not going to immediately make updates to the database based on the operations of that particular transaction. So we are going to defer those updates. And remember, we said that the transaction log keeps information about those particular changes that a transaction is making. So we can basically just have a transaction log of that particular transaction being recorded. And then we can actually now update our physical database after this transaction has executed to completion. And that way we are able to save some time, because you see, if this transaction does not execute to the end, then there is no need for us to be rolling back anything, because we never recorded that particular transaction on a physical database. So under right through, we are basically saying database is immediately updated by that transaction during transaction execution. And therefore now that tells us then should a transaction be able to abort before it is completed, then there is a need for a rollback. This is actually the opposite of the deferred right. So here is a transaction log for our transaction recovery example. So as you can see here, we have a transaction number 101 and 106. So 101 basically starts the transaction by accessing the table product. Then the row that is affected is ProdQOH. This is the value before is 45 and now it has been updated to 43. It makes access again to another table customer. The attribute that is affected is customer balance from 615.73 to 675.62, and then we end that transaction. Then now transaction 106 can be allowed to start, and it makes access to the invoice, and this is the value. These are the values that we have after. And then again, it makes access, because it's inserting, it makes access to line table, and it also inserts these particular values here we have at this end. And then we have an update again of product table, and we have a row, we have ProdQOH, which is affected. The value before was 12 and now it's changed to 11. Now we can have a checkpoint there, and then we can now proceed again with 106. We would access customer table and then affect the attributes customer balance. The value before was 0, now it is 277.5. Then we have it again accessing account transaction and to insert some data, and these are the values that we have, and then we end that particular transaction. And now again we can start another transaction 155, and 155 basically just accesses a product table, and then it makes updates to this attribute here, ProdQOH. The value was 6, now is changed to 26, and then we have end of that transaction. Then somehow the whole thing crashes, and a database checkpoint wrote all the updates to database buffer to disk, which is only for T101. Yeah, this point T101, it's for T101 because it's only T101 that was able to at this particular time end the transaction. So for T106 the transaction ends somewhere down here, so it's not yet written. So last checkpoint was 423, and the 423 is right here. 423, that's the checkpoint that we are talking about. So T101 started and finished before the checkpoint, so all changes were written, and then 106 and transaction 155 committed after the last checkpoint, so they will have there, that is after values written to disk using the log because of that crash, of course. And that marks the end of that particular topic. So see you next topic.